since this Monday, we started our new topic, natural convection. We didn't talk anything about gravity in external flows because the flow is driven by external forces like a fan, a pump. Right? But in natural convection, your flow is driven by buoyancy, which caused because of the density difference, and that's typically caused by the temperature gradient. We introduced a new material property termed the volumetric thermal expansion coefficient beta, and for ideal gas, beta is directly 1 over its absolute temperature. And for other fluid like water, we check the value of beta from the appendix in the textbook. And we talked about laminar free convection on isothermal vertical plate and the development of both viscous boundary layer and thermal boundary layer. Similar as external flow, free convection also has laminar region and a turbulent region. What's a critical number? Then we discussed 2 new dimensionless parameters. The first one is the Grashof number. Which is the measure of the buoyancy over that of viscous effect we use simply the product of Grashof number and the Prandtl number has a new name termed the Rayleigh number. And the Prandtl number is a ratio of viscosity to thermal diffusivity. They have very similar expression, but a little bit in the here as the product of kinematic viscosity and thermal diffusivity. And we discussed that the transition of the turbulence happens at the critical Rayleigh number is like 10 to the power of 9. And based on this, we can solve for the location along the vertical plate for where the turbulence starts. For laminar free convection, we can have the analytical solution to local Nusselt number, and as it shown, you need to solve the coupled equation of momentum conservation and energy conservation. It's super complex, but as it is provided in equation 9.19, the local Nusselt number, subscript x, which is by definition the local convection coefficient times its location over the thermal conductivity of that of our fluid, is a function of both Grashof number. At the figure on the left, that's the velocity profile. 0 on plate. Far away from the plate, that's 0 because the air is stationary at the beginning. And temperature profile, Ts on the plate, and as shown on the right figure, and decay exponentially, similar as what we have for external flows. Local Nusselt number is a function of both Grashof number and Prandtl number. That's what equation 9.19 says. Here because it can also be clearly seen from the graphs that the velocity distribution or temperature profile also has a strong dependence on what kind of material it is. Whether you have air or something else, that depends on Prandtl number. We use G Prandtl to show its dependence on Prandtl. It has a very complex interpolation form for the dependence for Prandtl number applies from all range of Prandtl number. But when we look at the interpolation here, I don't have. You do not need to memorize this, as all these guys will be provided in the formula sheet. For when we have something like water, for the case of Prandtl number larger than 1, like water, like oil, if we look at the here, see, okay, above we have Prandtl, square Prandtl, right? For large Prandtl number, along those super complex expression, which one dominant? We have a constant 0.6. We have a constant more or less 1 times Prandtl square. And we have another constant more or less 1 times Prandtl itself. And the whole thing to the power of a quarter. For the case of water and oil, maybe for Prandtl larger than 1, which term inside the complex guy, which term dominant? The Prandtl number, right? This guy here. And we have 2 is square above a quarter if this one dominant below. So for Prandtl number larger than 1, your dependence on function on Prandtl number is proportional to a quarter of Prandtl number. That helps you guys understand. We don't need to remember those super complex interpolation. But for Prandtl number smaller than 1, the same for above. But now you have a 0.6 here, and the Prandtl number square, Prandtl number itself. Above now, this constant 0.6 dominant, and a constant over constant. For Prandtl number much smaller than 1, your dependence on Prandtl is proportional to the numerator itself, to the square of Prandtl number. And that's it. If we look at this guy here for local Nusselt number, if we expand the expression for Grashof number, we have local, if we for x here, local Grashof number now to the 1/4. Your local Nusselt number is proportional to x, to what kind of power there? X square, x quarter, x a quarter. But Grashof number, you have x cube x there, right? And proportional to Grashof number to a quarter. Your local Nusselt number is proportional to 3/4. If we simply by expanding the definition of Grashof number. If you simply do an integration by, let's say, something like that, and I have put everything step by step in the note. For any of you may be interested, you can do the integral step by step. But the conclusion is that because the local Nusselt number is proportional to x to the power of 3/4, your average value in laminar region is simply the 4/3 to that of your local value. I don't put x here, x bar here, because x means a local value. Your average Nusselt number over a range, a plate, vertical plate with height of L, the average value in laminar region is simply by the 4/3 times that local value. That's given, start from here. And this correlation applies for both heating and cooling case. We don't have different exponents for heating and cooling as in external flow. For this one, it applies for all cases, but when you want to use this applies only valid for laminar flow. Then we will talk about the effect of turbulence. If our Rayleigh number exists that critical value of 10 to the power of 9, there is no theoretical solution like in laminar region for our turbulence. We need to go correlations based on experimental measurements. The average Nusselt number is typically has a form as a constant coefficient times some exponent to the Rayleigh number to some power. For laminar case, as we just derived here, and which gives us for laminar region is as a quarter for laminar, and based on experiment, and is a third for turbulent, and we will see those exponents flow around very often in many experimental correlations. Something I would like to catch your attention here. If, for example, we have our turbulent flow, and we know, I know that for my local Nusselt number now, it's proportional to Rayleigh number to 1/3. What does this just correlation? It means nothing. But if I have an exponent of 1/3, what does it imply? It's turbulent because of Rayleigh number larger than 10 to the power of 9, right? How would the thermal boundary layer develop? How about our convection coefficient? Typically, we have G beta delta T. If we expand the expression for Rayleigh, we have G beta delta T, nu alpha, all properties are constant. What matters is the air, the characteristic length you put there. Air is the length of the plate. X is a local length, right? To 1/3 means what? It's proportional to air square, or to air 3/4. I know this looks scary with so many equations, but they are just a constant. Look, G beta delta T nu alpha, they are just a constant. But something very scary is air, right? Air cube, and then for turbulent, we have 1/3 outside. Our average Nusselt number in turbulent region is proportional to the length of to the height of the vertical plate. Let's start with the definition of Nusselt number. We have Nusselt number. That's the dimensional value of convection coefficient. If I put air here, which means you need to use air as your thermal characteristic length over K of that of fluid, right? For average Nusselt number of air, let's simply have a bar here, the average convection coefficient times the air over the thermal conductivity of any whatever of the fluid. If in turbulent region, as we just discussed, this guy, the average Nusselt number is proportional to air. What conclusion can we get from there? The coefficient of air is a constant. And if it varies along the length of the plate, how can you give a linear proportional to the length of the air, right? Typically, your air thermal properties do not change that much along the length of the plate. In turbulent region, your average convection coefficient is a constant, which is independent of air. look at let's see, this is a vertical plate at a higher temperature of that of the stationary air surrounding. And let's give it Y here, and this is X. If I say, let's consider it's a combined case of laminar and turbulent, how would the thermal boundary layer develop? We know for heating case, it starts at the bottom of the plate, and the transition happens when your Rayleigh number equals 10 to the power of 9. And when it reaches to turbulent region, how would the thermal boundary layer look like? How H related to thermal boundary layer? Constant, right? Because H is a ratio of K over our YCT, thermal boundary layer. More or less, you have constant YCT in turbulent region. That's kind of not that intuitive to understand, but it comes from the exponent of 1/3. And for the isothermal vertical plates, correlations there are two solutions available. Let's see this one first. Applies for the entire range of Rayleigh number, 9.26. It applies for both laminar and turbulent region. It looks a little bit scary. And if we have our Rayleigh number smaller than 10 to the power of 9, you can use equation 9.27 directly. You see here, must check the condition before you use those correlations. For Rayleigh number smaller than our critical value, this one gives a better accuracy in laminar region. But if we check our Rayleigh number first, then end up with turbulence, you can only use 9.26 only, because this range does not apply for turbulent region. And if we, for example, let's see equation 9.26, if we have a quite large Rayleigh number, the first part gives us a constant. The second part here, we have Rayleigh number about to the power of 1/6, and a dependence on Prandtl number. But for a given fluid, Prandtl number is a constant. If Rayleigh number is pretty large, which term is larger? This constant term or our Rayleigh number term? Your Rayleigh number term dominates for very large in turbulence, and you have 1/3 here, 1/6 here, then the whole term square. It is consistent when we have turbulent flow. Your exponent is 1/3. Those equations are not random. They are consistent. Let's see when we have pretty small Rayleigh number. Now your constant term dominates. And in laminar, the same. For very small Rayleigh number, constant the 0.68. And here we have 0.825 square. There is a square here. You know what? The 0.25 square is exactly 0.268. So those two solutions are consistent with each other in laminar region. But just the above one is a little bit more accurate. But when we turn to turbulence, 26 only.